Now let's talk about the second part of the fundamental theorem of calculus, which is how we actually end up calculating any formula-based definite integrals, usually. If we have definite integrals from data, we tend to use methods more from chapter 5.5, but if it's formula-based, like sines and cosines and square roots and stuff, this is what we're going to be doing. So the fundamental theorem of calculus part 2 says that the definite integral from a to b of f of t dt, or some function, is the antiderivative, or any antiderivative at b minus that antiderivative at a. So in chapter 5.1 we saw indefinite integrals defined as antiderivatives. In chapter 5.2 we saw definite integrals defined as area under the curve. And now finally we're seeing the link between those two things, why it makes sense to write the integral sign for both of them. Let's do a quick example. Let's say f of t, little f of t, is the arrival rate of customers to our store, or to a festival, or to an emergency room or something, measured in people per hour at time t. What would this integral represent? The integral from 7 a.m. to 11 a.m. f of t dt. That would be, think about it, the number of people who arrive between 7 a.m. and 10 a.m. So that's accumulating the net change in people between 7 a.m. and 11 a.m. So that's just how many people. So that's the number of people arrived between 7 a.m. and 11 a.m. Another way we could write it would be capital F of x is the integral from 7 to x f of t dt, which would be the number of arrivals between 7 a.m. and x. Just the same way we had 11 here, now x is in the upper end, so we'd say between 7 a.m. and x. X a.m. So then, what is capital F of 11? Well, you can just plug 11 in for x, so it's the number of people arrived by 11 a.m. starting at 7, which is exactly what we talked about before. So it's the number of people that arrived by 11 a.m. starting at 7 a.m. So that's exactly that thing. But now we can ask more interesting questions. How about the integral from 8 to 11 a.m. f of t dt? What do you think that might be equal to? Is that just the number of people arrived by 11 a.m.? Well, that over-includes the people who arrived between 7 and 8. We don't really want to include them. So big F of 11 includes the people who arrived between 7 and 8, but this integral doesn't want to include them. So we don't want to count those people. Let's say that was an extra 100 people. What could we do? So here we'll say, nope, this over includes we don't want to include the people who arrived between 7 and 8. So for example, what if we had 400 people arrive by time 11, but 100 of them had arrived between 7 and 8? How can we uninclude them when we accidentally overcounted them? Well, we'd say take f of 11, total number of arrivals by 11 a.m., and subtract all the people who had arrived between 7 and 8, and big F at 8 is the number of people who arrived between 7 and 8. So that's why the fundamental theorem of calculus part 2 kind of makes sense. we're saying f of b is the total change so far by time b, kind of since the beginning of time. We haven't really specified, but we want to subtract off anything that happened before time a, and that's what we're doing here. Another way to think of it would be to say, if I have t and the f of t, let's say 7, 8, 9, 10, 11, and let's just say it's 100 people per hour. So f of t would be the number of arrivals by time t. At 7 a.m., how many arrivals have happened since 7 a.m.? 0 of them. At 8 a.m., how many arrivals have happened? 100. At 9 a.m., how many have happened? Those 100 plus those 100. So 200. And then 300 and 400. So f of 11 would be 400. F of 8 would be 100. And subtracting those will give you the 300, which would be this 100 plus that 100 plus that 100. So that's the logic of what's going on in the FTC part 2.